just start now. In the last class, I think one of you told that it would be better if we solved more problems. So I have tried to collect a few problems regarding this, related to this topic, and today we will be solving those problems. Right. So today will be mostly a problem solving session, and I have, I think, a total of around 10 problems, more or less. So yeah, we will try to cover this up in around 1.5 hours. So please hang on a second. I will just share my screen. Can you please tell if my screen is visible?
No, sir.
Screen is not visible.
No, sir. Hello.
Yeah.
No, sir, not visible.
Not visible. Just a second. Please share it. Now is it visible?
Now came and went up.
Now also it isn't visible.
Now visible.
Now visible now?
Yes, sir.
Okay. Okay. So as I told, we will see some problems, right? So I'll just take new slide. If you have copies, you can also note down problems as we solve them. Okay. So okay. So the first problem is, okay, so this is a pretty simple one. So I'll just write the problems as well. Yeah. So the first problem is this. For a SiC MOSFET, the device capacitances are input capacitance equal to 571 picofarad, output capacitance is 39 picofarad, and reverse transfer capacitance is 19 picofarad. Okay, so determine the values for CGS, CDS, and CGD. So can you try solving this? So you know that I will also solve, but I would encourage you to solve. Okay, so you know that the device model in terms of its capacitances, correct? So the device model in terms of its capacitances can be represented like okay. So you know that this is your CDS, right? This is your CGD, and this is your CGS. Okay, and this is your gate, drain, and then source. Okay, so they have given you your input capacitances, which is CISS, output capacitance is COSS, and reverse transfer capacitance is CRSS. So I think in one of our previous lectures, probably in lecture 1 or lecture 2, we saw how to find out these input and output capacitances, right? So input capacitances basically seen from your gate source terminal or the input terminal, correct? So input capacitance is seen over here with the output shorted, correct? And similarly, COSS or the output capacitance is the effective capacitance seen from the output side with your input shorted, correct? And CRSS is basically your reverse transfer capacitance, which is between the input and output. Okay, right? So with this information, with this information, it is pretty obvious that your CRSS is going to be the same as CGD. CRSS is equal to CGD. Therefore, CGD is 19 picofarad. Okay, which is this CRSS. So now what about CISS? CISS is nothing but, so CISS is the effective input capacitance with output side shorted, right? Effective input capacitance with output shorted, correct? So CISS is nothing but CGS appearing in parallel with CGD, right? Why? Because output is shorted, so therefore drain and source are short, correct? So CGS in parallel with CGD, which is CGS plus CGD, right? And similarly, COSS is going to be the effective output capacitance . with input shorted. Correct. So COSS is going to be CDS in parallel with CGD, right? Why? Input is shorted means gate and source are shorted, because G and S are short. So this is basically CDS plus CGD. Okay. So till this point, is it fine? That is how we are defining CISS and COSS. So if this is fine, then the final output that we want is going to be simply solving two equations, right? So CISS is basically CGS plus CGD. We just saw that CGD and CRSS are one and the same. Okay, so CISS is CGD. So COSS is CDS plus CGD, and CRSS is equal to CGD. Okay, so CRSS was, I think, 19 picofarad, right? So CRSS is 19 picofarad, right? So from this you can write CISS is given to be 571 picofarad. Okay, so 571 picofarad is equal to CGS plus CGD, which is 19 picofarad. Therefore, your CGS turns out to be 571 minus 19. Okay, is this fine?
Yes, sir.
Similarly, your COSS is given to be 39 picofarad. So COSS is basically CDS plus CGD. CGD is 19 picofarad again. Therefore, your CDS turns out to be 20 picofarad. Okay. Okay. So I think this is a pretty simple problem, but one interesting thing that you should note is that in all devices almost you will see CISS more than COSS more than CRSS, or I can also write this as CGS more than CDS more than CGD. This is a trend that you will see almost universally for all devices. Okay. Okay. So is this fine? Then if this is fine, we can go ahead to the next problem. Okay, I'll just open the next one. So okay. So the next question is, So the next question is, why is the apply gate voltage higher than the Miller plateau during turn on? Right? To increase current rise time, to increase voltage fall time, to reduce the on state conduction loss, to reduce threshold voltage. Okay, so can you tell the answer for this question quickly? Why? Why is the applied gate voltage higher than the Miller plateau?
I think to reduce the conduction loss, because for operating with higher gate voltage, less RDS on will come.
Correct. So for this, if you see the output characteristic of any device, right? If you see the output characteristic, what you will see is, let's say this is VDS and this is IDS. So this is the output characteristic of any generic MOSFET, right? So in that case, you will see that the output characteristic is something like this. Okay, this is not exactly according to scale, but okay, so let me redraw probably properly. Okay, not exactly according to scale, but I think you get the idea, right? So in this, you of course know that this is for increasing values of VGS, right? So this is VGS1, VGS2, VGS3, and this is VGS4. So we of course know that this is for increasing values of VGS. It is VGS4 more than VGS3, more than VGS2, more than VGS1, right? So one characteristic feature you see is that during the ohmic region, right? That is, what is the ohmic region? So the linear period or the profile where you see a linear increase, right? So this region is kind of your ohmic region, right? So this is your ohmic region, or you may also call it as linear region, where you can approximate the MOSFET channel as a RDS on, right, as a resistance. Okay, so this region is your saturation region beyond this. Okay, so in this region where you want to operate your MOSFET, you see that your VDS is very small, right? You're over here, somewhere around here, correct, during your ohmic region. And what you see is that the slope is actually varying for different gate source voltages. So for instance, the slope is this, for VGS1, slope is this for VGS2, then the profile is like this for VGS3, and profile is like this for VGS4, right? So you see, it's like 4 different lines, correct? So yeah, something like this. So what is the slope? The slope for all these lines, right? So the slope is basically delta IDS divided by delta VDS. That is y by x, right? Y by x. Okay, y axis by x axis. So that is delta IDS by delta VDS, which can also be written, right? Which can also be written as 1 by RDS on. Okay. So you see that for higher value of gate source voltage, the slope is increasing, right? Slope for 4 is more than slope for 3, more than so on, right? So if the slope increases, obviously it is slope is 1 by RDS on. Therefore, RDS on in 4 is less than RDS in 3 less than RDS in 2 less than RDS in 1, right? So you want to operate the device somewhere around VGS4. Okay, you want to operate the device somewhere around VGS4. You don't want to operate it VGS3 or VGS2 or VGS1, right? So you want to operate at a high gate source voltage. So if you operate at high gate source voltage, what happens? Your RDS is actually decreasing, right? So if your RDS decreases, then obviously your conduction losses are going to decrease, right? Conduction losses decrease at higher gate source voltage. Okay. Okay. I think this is again a simple problem. Let's go to the next one. Um, okay. So okay. So let's go to a series of questions, right? So this is a numerical question. Okay. So the gate voltage supply applying to the device mentioned in question 1, right? Question 1 is where we solve the device capacitances, right? Is 0 volts and 20 volts. Okay. So what do you understand when they tell the gate voltage supply to the device is 0 volts and 20 volts? So what does the 0 volt and 20 volt signify over here?
The gate pulse level.
Correct. So this is your let's call this as VEE, and this is your VCC. So if the gate voltage is 0, it means pulse is 0, or you want the device to be off, and obviously when the gate voltage is high at 20 volts, you want the device to be on. Okay, right. The Miller and threshold voltages of the device is 9.5 volts and 3 volts respectively. So the Miller voltage and threshold voltage are given for the device. The gate input resistance of the device is 13 ohms. Okay, this is the RG. Okay, so the device was blocking 625 volts, right? So this was the VDS before the device turns on. So this indicates your VDC or the DC link voltage, right? Is 625 volts, and the on state current is 20 amperes. Considering the first order approximate model of the gate transient and the following. Okay, so before we go to the subsections, let us understand what's given in this problem. Okay, so anyway, we know what is CGS, CGD and CDS, right? CGS, CGD, CDS, all of these are known from problem number 1. Okay, and the Miller, let's call it V Miller, is 9.5 volts, and the threshold voltage of the device, or the device at which the device or the voltage at which the device turns on, is 3 volts, right? The gate input resistance, or RG, is given as 13 ohms, right? And the VDS that it was blocking is going to be 625 volts, and the on state current, or ID, is given as 20 amperes. Okay. So considering the first order approximate model of the gate transient. So what do you understand by this? First order approximate model of the gate transient. Any idea? What do they mean by first order approximate model of the gate transient? Okay. So we just saw that, let's go back to the device, right? So we just saw that the device has parasitic capacitances. Correct? They have given an RG, right? And then it can be connected to the pulse. This is connected to the source, right? So this is your, okay, so let me take a different ink over here. So This is your VG, right? This is your RG. This is your CGS, CDS, and then CGD. Okay. So now you can understand that looking at the gate side, right? Looking at the gate side, this is a first order network, right? How is this a first order network? The gate side equivalent circuit can simply be represented as something like VCC, which is 20 volts. This is RG, and this is CGS, right? So this is your first order approximate model. Okay, because we saw in one of the previous classes that there can be parasitic inductances due to which you will generally Kelvin kind of have a Kelvin connection, right? So there can be parasitic inductances. So if you're going to include these inductances, then what happens is this is an RLC network. So there is RG, then CGS, and then there are also parasitic inductances. So if it's an RLC network, it becomes a second order network, right? So they have told us indirectly that you can neglect these parasitic inductances. Okay. So neglect these parasitic inductances. If you neglect these parasitic inductances, you're just left with an RC circuit. Okay. So this is just an RC circuit, and you know that the voltage across this capacitor is basically VGS, right? Voltage across the CGS capacitor is your gate source voltage, okay, VGS. And eventually, since this is an RC network, what will happen? So forget about all these gate transients. If you just take an RC network and connect a DC source, right, that is VCC, eventually the voltage across VGS is going to charge up, right? Voltage across the VGS is eventually going to become how much? So let me tell this as capital VGS, right? So capital VGS initially, right, was 0 volts. Correct? Initially, the gate source voltage was uncharged. Why it was 0 volts? Because they have given that the gate voltage supplied to the device mentioned in question was 0 volts and 20 volts respectively, right? So 0 volts is VEE and 20 volts is VCC. That is when the device is off, right? Gate source voltage is 0 volts. If they had given us -5, you have to consider the initial condition as -5 volts. So over here, you understand that VGS at 0 minus is going to be 0 volts, and VGS at t equal to infinity, right? After in not exactly infinite time period, just for the sake of mathematics, I'm telling this, but once the turn on process is complete, right? After the turn on delay time, or let me time right, this is for t more than the turn on time, you will get you will get VGS is equal to 20 volts, correct? So this is your final condition, and since this is an RC network, you know that the profile of charging of VGS is going to be what? Is your DC voltage VCT into 1 minus e power minus t by tau, correct? Where tau is equal to Rg into CGS, right? This is the profile of charging of your VGS. This is how your VGS is expected to increase. Is this fine? Can you please tell me if this is fine? Or do you have any objections, like is there any mistake that we have done or anything? Is this fine?
Impedance, how sir? RG multiplication combo, not combo.
Yeah, so tau is basically the time constant, right? It's your RC time constant. It's just an RC circuit.
Okay, it's
So
a
you
time
understand
constant.
that in steady state, the voltage across your gate source is going to become same as VCC. And initially the voltage was 0. And since it's an RC network, your profile of increase would be an inverse exponential, right? So 1 minus e power minus t by tau. Correct?
Okay, sir. It's
So
tau. Okay, it is tau
Yeah,
I
yeah, tau,
actually.
tau, yeah.
Okay, looks like.
So you will be seeing something like this, right? I mean, not exactly how I have drawn, but so you might see something like this, correct? It will eventually reach steady state, right? Just an RC network. Forget about the dynamics. I mean, the device dynamics. Okay. So at least in the initial stage, when the device is going to start, right, the profile of VGS increase would be something like this, right? Okay. So one thing that you guys need to take care of, in the first problem we saw what was the effective input capacitance, right? So input capacitance is 571 picofarad, right? And what is the effective input capacitance? Effective input capacitance is the capacitance seen from the input side with the output side shorted. Okay, fine. So during starting condition, right? During starting condition, what happens is, yeah. So the current over here, right? The current over here is actually getting two paths. One is through CGD, right? And the other is through CGS. Okay. So effectively what you would see during starting alone is that your CGD and CGS are going to come in parallel, right? So your tau is basically RG into CGS plus CGD, right? Or RG into CISS. Okay, this is your exact value. But since the value of CGD is very small, people generally do not consider this, right? People directly write RG into CGS, which is absolutely fine. Okay, fine. So the first part of the question is, yeah. So the first part of the question is, what is the peak gate current during turn on? Okay, so can you answer this? Just think in terms of an RC network. So what is the peak gate current in the circuit? Just take this circuit, okay? So what is the peak gate current? Or what is the peak current that would flow in this circuit?
1.54 amps.
I mean, not the exact value. You may be right, but we'll just derive it. Like, how do
Means
you
that
find it?
maximum gate pulse height when it is on, so 20 volt by external gate resistance.
Correct. So your peak current, right, or IG peak, if I call it, it is going to be simply VCC divided by RG, right, which is 20 volts divided by what was the gate resistance? 13 ohms, right? So what was the value, please? 1 point.
1.54 came 538 like that.
Okay, so 1.54 amperes approximately. So you understand that initially the capacitor is kind of uncharged, right? So initially, as we wrote over here, VGS 0 is 0. So initially capacitor is uncharged. So I should not write capacitor. Initially, CGS parallel to CGD is uncharged, correct? Therefore, we just saw that VGS of 0 minus is 0 volts, right? So since they are uncharged, you can take that it's a direct short, right? CGS and CGD is directly shorted. Therefore, the equivalent circuit simply becomes VCC and then RG, right? Okay. So let's say instead of 0 volts, they had given this is minus 5 volt, right? Let's say this was minus 5 volts, the other case. Let's say this was minus 5 volts. Everything else is same. So let's say this was minus 5 volts. Then what would change?
Change.
The peak to peak swing will become 25.
Peak to peak swing will become 25, correct? Right? So you would understand that your IG peak, right? In this case, if your VGS was minus 5 volt, your IG peak would be VCC minus VEE divided by RG, correct? So what is this VCC minus VEE? 15 minus of minus 5 divided by RG is 13. Okay, that is, sorry, so this was 20, right? Yeah, so 20 minus of minus 5 by 13, which is 25 by 13, almost 2 amperes. Okay, and similarly, if you can recall your analysis from circuits, you would know that this VGS, since it has an initial condition now, it would be written as VEE plus VCC into 1 minus e power minus t by tau, correct? In this case, where VEE is minus 5 volts. Okay, is this fine with you guys? So this particular graph, instead of starting from 0, it would be starting from minus 5 and then slowly it will go to this. Do you understand this? Is this fine?
Yes, sir.
Okay. So one thing is, people generally prefer keeping a negative voltage of minus 5 volts, because we also studied that in week 3, I guess, wherein we try to have a negative gate source voltage so as to avoid spurious turn on or false turn on of the device due to high dV by dt transitions. But one drawback, as you can understand over here, is that if you have a negative gate source voltage, you are going to have a larger gate swing, as he told, right? There will be a larger gate swing. Therefore, the peak gate current requirement is going to increase, right? And where is this gate current coming from? The gate current is coming from your source, which is VG. So the gate current is coming from your source, right? Or your gate driver. So your gate driver has to be rated for higher current. So gate driver has to be rated for higher current. If the peak current is 2 amperes, you at least want a gate driver that can give you 3 or 4 amperes, right? So this is something that you need to take care while doing your system design. Okay. But one advantage with gallium nitride devices is that with gallium nitride devices, or GaN HEMTs as we call it, right? You would see that the VCC is just 6 volts almost, and VEE is generally minus 3 volts. Okay. So for the same gate resistance, right? For the same gate resistance, let's say 13 ohms, you would see that the peak gate current requirement, your IG peak, is going to be VCC minus VE by RG, which is 6 minus of minus 3 by 13, or 9 by 13, which is less than 1, correct? So the IG peak requirement decreases for GaN devices, right? And the reason is because the recommended gate voltage, we do not take it from 0 to 15 or minus 5 to 15. Rather, The recommended gate voltage is between +6 and -3. There are devices that have VCC of 5 volts and VE is simply 0 volts. Okay. So the IGP requirement is even lesser, right? So lesser burden on the gate driver. Okay. Fine. So we'll just move on to the next question. So what is the current rise time, right? 0 to 100% of the steady state current, and what is the di by dt during turn on? Okay. So before we answer this question, right, I think we have to go into a bit of yeah. Okay, so as I was telling, we have to understand what happens during the device turn on to answer this question. Okay, we cannot answer this directly. Okay, so you can understand that. Okay, so let me draw the plots. So let's say this is your VGS, correct? And this is your IDS.
The slide not visible.
Oh, slide is not visible. Okay, just a second. Is it visible now? Is it visible now?
No, sir.
No. Just a second. Now is it visible?
Yeah, yes.
Okay. Yeah. So this is your IDS and this is your VDS. Okay. So as we were talking, right? So your VGS would start increasing from VEE. In our case, VEE is same as 0 volts, right? So it would start increasing from VEE. For simplicity, even though I told that the profile of increase is VCC into 1 minus e power minus t, it's something like this. Let me assume that we are over here, therefore the rate of rise of the current is linear. I mean the rate of rise of gate source voltage is linear for simplicity. Okay. So gate source voltage increases, right? It would increase till this point, and at this point I have hit my threshold voltage. Okay, so this is my threshold. Okay, and you recognize that until the device hits threshold, nothing changes, right? Until the device hits the threshold voltage, gate source hits the threshold voltage, there cannot be any current at all, right? So the current is going to be zero till this point, right? And we saw that the voltage blocking was around 625 volts in the problem, right? 625 volts. So the device was blocking 625 volts till this point, correct? Until the device hits the threshold. Okay. Then what happens? So once the device hits the threshold voltage, right? The VDS initially was 625 volts, correct? The device hits the threshold. Okay, the gate source voltage hits the threshold. Now I will just go back to this particular output characteristic curve, and can you tell me just at this point, right? Just at this point when the device hits the threshold, before the threshold, the device was in cutoff region, correct? The device doesn't conduct any current. But once the device hits the threshold voltage, so in which region is the device operating in right now? Just when the device hits the threshold voltage, or just after the device gate source voltage becomes more than threshold.
Linear.
So in which region is the device operating?
Ohmic region or linear.
Ohmic region. So how are you telling it's ohmic region?
Because gate voltage is just touches means just hit the threshold voltage means it not crosses the overdrive voltage. So just
Correct. So
above the this thing.
okay. So mm, just a second. Yeah. So let's go back to the definition of device out operating characteristic. Okay. So one is the well-known cutoff region, right? In cutoff region, you know that your VGS is less than V threshold. So the device is totally turned off. So the IDS is zero, right? And VDS is very, very high, or it is blocking a very high voltage, or VDS is almost equal to VDC, correct? Next comes your on period, when the device is turned on, or when the device turns on. It can either be in the saturation region, right? Or it can be in the ohmic region. Okay. And yeah, so one more thing we saw was it's in the cutoff region, so the device is totally turned off. The equivalent resistance is some equivalent representation is something like this. Okay, and the device is turned off. So in the saturation region, you know that VGS is more than V threshold, but more importantly, what defines saturation region? You tell that a device is in saturation region only when your VDS of the device is much more than, right, much more than VGS minus V threshold. Okay, right? In this case, if this is the case, if VGS is more than V threshold and your drain source voltage across the device, right? Drain source voltage across the device is much higher than VGS minus V threshold. Okay, if it is much higher than VGS minus V threshold, then you tell that the device is in saturation region. In saturation region, if this is the condition, the device would be behaving like a voltage controlled current source or a dependent current source. Okay, it behaves like a voltage controlled current source. So your channel current, or almost your drain source current, is actually what? GM into VGS minus V threshold. Okay, so for a particular value of VGS, right, for a particular value of VGS, if your GM is fixed, if your transconductance, GM is your transconductance, right? If your transconductance is fixed for a particular value of VGS, the current is fixed. That is why we call this as a current source. Okay, this is your saturation region. Just for your information, GM is a function of temperature T. Okay, so for a particular operating condition, if the device is operating at, let's say, 70 degrees, there will be a particular value of GM, right? And if there is a particular value of VGS, right, then your IDS is fixed. Okay, this actually corresponds to the flat lines you see over here. Okay, the flat line that you see over here, the flat line that you see over here. Why is this flat? Why is this flat? It is flat because now it is behaving like a current source that is kind of flowing a constant current through it, allowing a constant current to flow through it. Okay, and you can understand that the condition we told was VDS should be much higher than VGS minus V threshold. That is this particular condition. You can understand that it is happening for higher values of VDS. Okay, fine. Did you understand what is saturation region? And third comes your ohmic region or linear region. Of course, this definition is only for a MOSFET. For IGBT, you know that saturation and linear regions are kind of interchanged in nomenclature. So in ohmic region, of course, VGS is more than V threshold, but more importantly, your VDS is less than VGS minus V threshold. So in this case, you can approximate the MOSFET channel to be a resistance called RDS on. Again, this RDS on is a function of temperature, right? This is something we know. RDS on is again a function of temperature. Okay, these are the three operating regions in a MOSFET, right? So consider this initial condition, right? This was the, yeah. So this was your initial condition, right? Till this point, I'm calling this as interval 1 till interval 1. So till interval 1, the device was in which region? Just before interval 1 or just before the instant 1, the device was in which region? Hello?
Cutoff region.
Cutoff region, correct. So after instant 1, then what is happening? After instant 1, the gate source voltage crosses your threshold voltage, right? Gate source voltage is just increasing beyond threshold voltage. So then the device will transition to which region?
Saturation region.
Correct. So when the device turns on, it can never turn on directly in ohmic region or linear region. It will always turn on in the saturation region. Okay. It will at the instant of turn on. Then from saturation, as VGS increases, it will slowly go to the ohmic region. Okay, so you understand that right now we are in the saturation region. So as threshold voltage increases, right? I mean, I'm sorry, as VGS increases, then what is happening? VGS increases, GM is fixed, right? GM is fixed, VGS increases, right? So VGS increases beyond V threshold. So as the difference increases, your current also increases. Okay. So let me take a different color. Okay. So your gate source voltage increases. following the profile of increase in gate source voltage, your current will also increase. Okay. I am assuming that increase in, as I told earlier, even though it's a 1 minus e power minus 3 by tau graph, I am assuming that the rate of increase is linear. Just an assumption for our simplicity. Okay. So this is linear. If this is linear, then if VGS increases linear, I know that the current increases as GM into VGS minus VTH. As VGS increases with time, similarly, my IDS will also increase like this. Okay, fine. What about VDS? Will VDS fall during this period or no? Will VDS fall during this period?
Yes, it starts to fall down.
So if I draw it, will it be like this or will it be another voltage like this, or how will it be? I'm sorry. Would it be like this or would it be like this? How would it be?
Linearly decrease, I think.
It will. So how are you telling that why would it linearly decrease? Why should it linearly decrease?
Because when MOSFET is tries to enters into saturation, and then based on its RDS on values, this VDS will
No, you forget about RDS on value. It's in saturation. If it is in saturation, there is nothing to do with RDS on, right?
okay.
So see, you
Yes.
can understand, right? If you are over here, you're over here, correct? So if you're in this slope, if you're in this region, then what is the slope over here? Slope is basically nothing, correct? So slope is zero. If your slope is zero, then RDS is infinity. It's like that's why we are modeling it as a current source, na? So if it is a current source, then obviously the resistance is infinity. It doesn't matter. It's a current source. Okay. So if it is in RDS region, we never talk about. I mean, if it is in saturation region, we don't talk about RDS on. It will be because the MOSFET cannot be approximated as an RDS on, right? I have written over here. It can be approximated as an RDS on only when it is in the ohmic region. When it is in saturation region, it's like a current source. Okay. So what would happen to the voltage? It's a current source now. MOSFET is a current source. So what would happen to the voltage? Why should it fall? If it will it fall? Number one, and why should it fall linearly? Number two, it's a question. Okay, so yeah. Okay, so basically, let's come back to the application, right? So where are we using this? We are using this in a half bridge application, something like this. Okay, so this is your buck converter. Okay, or let's say this is your double pulse test circuit. Okay, simplicity. Let's assume that this is your double pulse test circuit, or buck converter also will do anything is fine. Okay. So now what I'm trying to do is basically I'm trying to turn on S2. Okay, I'm trying to turn on S2. We are seeing the turn on of S2. Turn on transmission of S2. Okay. So initially, what was happening? Initially the voltage across drain to source, right? The voltage across the drain to source is same as VDC, correct? So this is your VDC. Therefore, initially the voltage across drain to source is nothing but VDC initially. Okay. And you know that inductor is a current stiff element. So the inductor current would have been freewheeling through the anti-parallel diode, right? Before the MOSFET turns on, correct? Inductor current would have been freewheeling through anti-parallel diode. So the inductor current is given as 20 amperes in our problem. So the 20 amperes was flowing through the diode. Do you understand this? Is this fine? What I'm explaining, is this fine? Do you understand? Prior to the turn on of S2, the inductor current was actually freewheeling through the anti-parallel diode of the top device. A similar argument holds good for turn on of S1 as well. Hmm. So do you understand this? Inductor current
Yes.
was freewheeling through the
Yes, sir.
anti-parallel diode of S2. Yeah, so as I was mentioning, just before your turn on, what was happening? The entire inductor current was flowing through the anti-parallel diode of S1, right? Just before the turn on of S2. Okay. So this is the case, right? So this is the case until instant 1. What is instant 1? Instant 1 is this. Okay. Then what happened? Then what happened was your gate source voltage increased beyond threshold. The gate source voltage actually increased beyond threshold, as a result of which the device started behaving as a constant current source. Right? The device started behaving as a constant current source, and the drain source current also increased like this. First of all, let me check if I'm there. Hello, is the audio audible and is the screen visible?
Yes, sir.
Okay, okay, thanks. Okay. So then beyond instant one, what happened was your gate source voltage increased like this, so your gate drain current also increases like this, and the device is behaving like a constant current source, right? So let's draw the equivalent circuit. So what happens in the next interval is yeah, what happens is so we told that during the next interval the device is behaving as a constant current source, right? Constant current source. Okay. So the device is behaving as a constant current source. Okay, so it's better I draw it as a MOSFET only. Okay. Yeah. Um, so your inductor current needs to be still constant, right? Your inductor current has come till this point, and what we see is that since the device behaves as a constant current source, right? So the current will now split, right? The inductor current will now split. Some part of the current will flow through this constant current source, right? And some part of the current will flow through the antiparallel diode, right? Right? So if let's say the total current is 20 amperes, right? The total current is 20 amperes, that is the inductor current. Total current is 20 amperes. Then what happens is initially it was getting split as, okay, so yeah, you can understand from this figure what was happening. Some current goes here and some current goes through the top device. So initially what was happening, the entire current flows through the top device and no current flows through the bottom device in case 1. Then what happened, the same 20 amperes will now, some part of the current will flow through the antiparallel diode, correct? And some part of the current will flow through the I channel, that is your constant current source. So now as the gate source voltage increases, this I channel will also keep on increasing. Okay, the I channel will also keep on increasing, correct? So I channel increases as VGS increases, right? This is something we saw. I channel is increasing, right? I channel or IDS increases as your gate source current, I mean as your gate source voltage increases, correct? So now as the total current is only 20 amperes, so what happens is the 20 amperes gets split as I channel and the remaining will go through the anti-parallel diode of S1, IS1, okay? Now what will happen is I channel will keep on increasing, keep on increasing. So as I channel increases, then what would happen is that your the current through the anti-parallel diode of S1 or IS1 decreases. Okay, and at some point what would happen is that at some point your entire 20 amperes will be carried by your I channel. Do you understand this? We were here initially, then the device turned on in saturation region. As the gate source voltage increases, your I channel will increase from 0 towards the rated current, which is 20 amperes. Is this fine? Is this fine so far?
Yes, sir.
So what would happen is that your initially we told that the current is getting split, right? It is getting split. So then at the end of this interval, you would see that the entire current has transferred to the device being turned on, S2. Okay. Initially the current was like this. Okay. Entire current would get transferred to the other device. Right. So this, the point at which your S2 starts carrying the entire load current, right? That defines the end of this interval. Okay. That defines the end of this interval. Let me call this as 2. Okay. So at this point, right? At this point, you have reached or rated IL, which is 20 amperes. Okay. So you started at 0 and you reach your rated. Okay. Now coming back to the question, what happens to VDS, right? That is where we started all of this discussion, right? So you tell me, initially we told that the voltage across the device is VDC, right? The voltage across the device is basically VDC. So what is happening over here? The current is basically getting transferred from the top device to the bottom device, right? And how is this transfer happening? The transfer is happening because the device is behaving as a constant current source and the other device is a diode. Okay. The diode is actually, if you see the path for the diode current, right? The current is flowing like this. The path for the diode current is through this, right? This is anode and this is cathode. Okay. The total voltage is VDC, right? The total voltage is VDC. Now you tell me when can the diode conduct? Under what condition would the diode conduct? The diode can conduct only if this voltage is more positive than this voltage. Agreed? Do you agree? The diode can conduct only if this voltage is more positive than this. That is, VAK should be a positive number, right? Do you agree? Do you understand this? Only then the diode can conduct. Do you agree?
Yes, sir.
Right. So only then the diode can conduct. So when would this be possible? It is possible only if the device is actually blocking some voltage across it. Right. The moment you tell that, let's say this is VDC. If let's say hypothetically this was VDC by 2, right? If this is VDC by 2, then rest of the voltage would appear across this device. This would be VDC by 2 again, right? Then it would render the diode not being able to conduct. The diode can conduct only if this is more than this, right? So what happens is, right? So what happens is you would see that the device continues to block whatever was the DC bus voltage. Okay. Until this instant, the diode, the device continues to block the entire DC bus voltage, which is VDC. Okay. Device continues to block the entire DC bus voltage. Until what point? Until the diode stops conducting. Until this particular diode stops conducting, right? Until this particular diode stops conducting, this device cannot block any voltage, right? S1 cannot block any voltage. Okay. So S1 cannot block any voltage. S1 cannot block any voltage. Right, you understand, right? If there is a positive voltage across this, then obviously the diode cannot conduct. You understand, right? Is this fine? Like my argument, is this fine? Do you understand? Until the anti-parallel diode conducts. Is this fine so far? Everyone like Selvakumar sir, Ravidas and Anandi.
Yes, sir. Yes, sir.
Why? It means because if there is positive voltage across this diode, it means the diode cannot conduct. Right? So until the diode stops conducting, or until the point at which the entire current goes to S2 and diode stops conducting, the voltage across S1 cannot change. Right? If the voltage across S1 cannot change, voltage across S2 also cannot change. Right? So voltage is being blocked by S2 only until S2 starts carrying the full load current. Do you understand? Do you agree with this?
Yes, sir.
Okay.
Yes.
Okay. So that is why your unfortunately this blue thing got saved over here, but that is why the DC bus voltage, that is why the DC bus voltage or the drain source voltage remains V. Uh, yeah. So that is why the DC bus voltage or the drain source voltage remains at VDC until your IDS hits IL, until this point. Until this point, your VDS will remain at VDC. Okay, fine. Now that this has happened, after this happens, then what would happen is that, so after this happens, now what has happened? Your entire current has transferred to the other device. Okay. There is no voltage across this. I mean, there is no current flowing through the diode now. Then what would happen is, initially the voltage was VDC. Slowly the voltage through this device will decrease and the voltage across S1 would increase. Okay. So that is what was shown in this figure. Yeah. So then what would happen is, slowly the voltage through S2 would decrease. Okay. Slowly the voltage through S2 would decrease and slowly the voltage across S1 would increase. Right? Okay. I hope this is clear. Okay. So after this, what happens is that your yeah. So after this, what happens is your drain source voltage would slowly decrease to almost zero. Right? Drain source voltage would decrease to almost zero. Okay. And what about IDS? IDS has hit IL now, so it can be constant. Okay. IDS has hit IL, so it can be constant. Okay, so okay, we will come back to what happens after 2 later on, but we will come back to the numerical problem, right? So numerical problem is the what is the current rise, current rise time and dA by dt during turn on. So they are asking us to find out what is T2 minus T1, that is this particular interval. They are asking us to find out this particular interval. This is known as TR or current rise time. The current is rising from 0 to IL. So what is TR they are asking, and dA by dt is simply, dA by dt is basically, if you find out what is TR, it is basically IL minus 0 by TR, which is IL by TR. This is your dA by dt. Did you understand the question? So with this question
Yes, sir.
itself, I think we have seen a bit about device dynamics. Generally, we tell that, okay, so when the device turns on, the current kind of increases beyond the threshold. So the current increases like this and the voltage falls like this. This is how we generally represent that. This is voltage VDS and this is current IDS. This is a very approximate model. And since we are doing a course on WBG devices, we need to know what exactly happens during turn on and turn off. Okay. So for answering this question, we cannot rely on the approximate model. We have to know actually what happens in the half-bridge circuit. Okay. Okay. So just give me a time for 3-4 minutes. I'll just have some water and come, and then we will resume solving this problem. Okay. Okay. So you can resume now. Yeah. So as I was telling, during this interval, what happened? Oh, what happened? Yeah. So during this interval, what happened? Your VGS, right? Your current increased from 0 to IL. Your VGS increased from V threshold, right? V threshold was the starting point to a point called V Miller. at the end of this interval, VGS reaches a point called V Miller. Okay, we saw in the problem that V Miller was given as 9.5 volts, right? V threshold is 3 volts. Okay, so it reaches what is known as V Miller. Okay, between during this current rise time, VGS increases from V threshold to V Miller. We have to find out this period, this time, right? That is, VGS is increasing from V threshold to V Miller. We have to find out this particular time. Okay, so how do we find that out? Any clues, any ideas? The hint is this: we look at, they have asked about current rise time, but during current rise time, we saw that um, the gate source voltage is rising from V threshold to V Miller, right? So can we find out from this? I hope I have
That
that.
exponential equation can I use for initial voltage from V1 to means threshold to V Miller?
Correct. So that is what we have to do. Okay. Just substitute over here. That is, we just saw some time back that your VGS, right? Um, VGS of T is basically what? VCC into 1 minus e per minus T by tau plus VEE. VEE is 0 in our case. Okay. Where tau is equal to RG into CISS. Okay. Now we have the boundary condition, right? VGS at T1, right? VGS at T1 is nothing but what? Threshold voltage, V threshold at T1, right? At T1, VGS is threshold voltage. So threshold voltage is equal to VCC into 1 minus e power T is basically T1 right now, T1 by tau, and VGS at T2, right? At the end of the current rise interval, right? At the end of the current rise interval, your VGS is V Miller or VM. Okay, Vm is equal to VCC into 1 minus e power minus T2 by tau. Okay, now we have to find out what is T2 minus T1. T2 minus T1 is the current rise time, right? TR, right? So we can solve these two equations, right? Solve 1 and 2 to find out T2 minus T1. Or a better approximation would be that instead of taking another variable called T1, what you can do is put T1 equal to 0 and T2 equal to TR, right? Because this we are finding out the difference between T2 and T1. So why to confuse ourselves with another variable, right? A simpler way would be that just put T2 equal to, T1 is equal to 0 and T2 equal to TR. By that way also you can directly find out what is the answer. Okay. Or as I was telling, so this is actually the accurate way of doing things. Okay. Accurate method. Right, so you may have to find apply some logarithmic methods to cancel out the exponential term, right? And then you can find out this is the accurate method. Or the other method is linearize VGS of T increase, right? The reason is, see over here, as I was telling, we can assume that VGS profile is linear over here. Okay, because your RC charging is something like this. So in the initial regions it is linear, and then only it becomes kind of flat, right? So let's assume we are in this region. Okay, so let's assume VGS increase is linear. So your current increase is also linear, right? If your current increase is linear, VGS increases linear and vice versa. Okay, then it is even more easier, right? This is just a straight line, right? So this is just a straight line with coordinates being what? Coordinates being, let's say this is time 0. This is 0 comma V threshold, and this is simply TR comma VM. Do you agree? Is this fine? I have just written the coordinates for VGS. From this also you can find out. So we have something like this. This point is 0 comma V threshold, and this point is yeah. Unfortunately, my computer is troubling me a lot today. Okay, so you understand that if you assume that the VGS profile is linear, so then you end up with this being the point of TR comma V Miller, right? So from this also you can find out what is your you can find out what is TR. Okay, if you assume that the profile is linear.
Excuse me. So this graph you made, na? So starting from this T1 and up to where your this VDS is become 0. So means till that much overlap time your energy will be lost, huh, for turning
Correct.
on the
Yes,
switch.
yes, yes, of course, yes.
Okay, so means irrespective of means instead of DPD test, I'm telling, means for example your class D sub-bridge class D configuration if it is there. So this time duration will be same for that, as you said, na, this load current first have to shift to S2, then it will
Yeah,
become.
so in any case of a clamped inductive load isn't like something like this. If there is a constant current source which is connected at the switching node, right? This is like a constant current source, you know, 20 amperes is constant. So if there is a constant current source connected at a switching node, then you are expected to see something like this. Okay. If
Okay, instead of like your buck converter also, it is similar
uh-huh.
fashion of a class D amplifier. In that
Mhm.
case also it will be same, huh?
Correct. If yeah,
Okay.
yeah. If you are dealing with a half bridge network and yeah, if you are dealing with a half bridge network with a constant current source, you will see this because primarily you will see the diode being conducted in the antiparallel fashion. So in that case, obviously, the diode cannot block voltage unless it stops conducting. So that's why you will see this profile. So if you
So
have to evaluate the losses,
any
exactly you
means
have to take both of these intervals into consideration.
okay means then any methods is there to reduce this loss or energy losses, switching loss? Means overlap
Uh,
area you can reduce anything
Correct.
is there?
So there are a lot of techniques actually. So this is called a hard switching loss. Okay, hard switching loss. As in like you will face, as you were telling, you will face losses in this area, correct, and also in this area. Why? Because VDS and IDS are overlapping over here, and VDS and IDS are overlapping over here. Okay, either of one of these needs to be zero for losses to be zero, switching losses to be zero. Correct. So in order to reduce this, you have to basically reduce this TR time and this voltage fall time. This interval and this interval need to be reduced. One of the methods is what generally people do is reduce your gate resistance RG, right? If I can fasten up this profile, if I can fasten up the profile of increase of VGS, right? Then I can make sure that current also increases quickly, right? So my rise time of the current is going to decrease, right? This is a very simple method that people follow. That is, they will just reduce the gate resistance RG. Therefore, your switching losses are going to reduce. Why? Because your overlap time will reduce. Is this fine? This is one. Second
Okay.
one is what is known as zero voltage switching, or people call this as soft switching. Okay. So there is something, okay. So in ZVS, what you try to do is you try to avoid this overlap. Hmm. That is what I will do is I will try to somehow shift this instant of current rise. Okay. I will try to shift this instance of current rise by making sure that my current will start increasing only after my voltage has gone to zero. Right? So something like the voltage will first go to zero, and when my voltage will go to zero, I will start increasing my current. So there is no overlap. Okay, there are techniques, but I think that is beyond the scope of this course. Okay, but yeah,
Means
there are
some
techniques. So this
constantly your this voltage VDS or current you need to sense and based on that you make some feedback like that, huh?
kind of. There are also auxiliary circuits that will kind of bypass the current. So we saw that the main culprit was this, right? The antiparallel diode being conducting, right? So the question is, can I find out an alternate path, right? Can I find out an alternate path so that the current not necessarily flows through the diode? Okay. So yeah, but I think that is out of the scope of this course. Actually, I think there
Okay,
was a
okay, sure.
separate course for us called based on this short switching technique. If you want more information, I can take one course. I mean, one session for that, but that would become kind of personalized. If others are also interested, then I can perhaps handle one session on how to do the short switching. But it is out of scope of this course right now.
Okay, okay, sure. Fine.
Okay. But yeah, I mean, if you want to operate at high frequencies, you have to go for ZVS. You understand, right? Because you have to decrease your overlap time, correct? So, I mean, if you want very basic reference materials, there are a lot of materials available online on just basics of ZVS and how people do it. Okay. Okay. Um, but yeah, but there are applications where you cannot apply ZVS. Okay, there are applications where you cannot apply ZVS. In those instances, you have to depend only on reducing RG. Hmm. So the ZVS is applicable only for resonant converters, as we call them. Okay. So there will be an LC resonant network, and you try to match your frequency. I mean, that is your switching frequency with the LC resonance of the system. Okay. So see over here, right? Yeah. So over here, you assume that your L is very, very large. That is the assumption. L is very, very large. Therefore, this is a constant current source. Okay. What if I make my switching frequency very high, or I will not tell very high. What if I make my switching frequency so that it matches the resonance frequency between your load inductance and the device capacitances? So there will be a resonance frequency due to the load inductance and device capacitance, right? I will make my switching frequency very equal or very close to that resonance frequency. Okay, in that case, you would see that the inductor current is no longer a fixed DC. You will see, since you are operating at a very high frequency, you will see that the inductor current actually varies something like this. Correct? Sinusoid. And I will make my switching frequency also like this. So then what is happening? I will turn on my device at near the zero crossing of current. Correct? So naturally, I will be getting a ZVS. I mean, this is a totally out of scope. So just to give you an idea, I told. So they are known as resonant converters. Hmm. That is one way of doing it, ZVS. There are multiple ways though. Okay. Okay. So yeah. So we were over here. That your VGS will basically increase from V threshold to V Miller, right? So you can approximate this as a straight line and again find out, right? So how do you find it out? Okay, so till this point, is it fine? Like what we did, that is based on these two equations. If you solve, you can get what is your TR. Okay, fine. I'm not solving it. Okay, in the interest of time. So the next question is about how do you find out the voltage fall period, right? That is, how do you find out this particular period? That is between 2 to 3. Okay, how do you find out this particular period? Okay, so for this, again, we have to understand what happens during voltage fall period. I will explain physically what happens, right? And the problem part we will continue solving from the next class. Okay, so what happens is, see, so till this point, I guess you're fine, right? Now let us go back to the capacitance model that we were drawing, right? So um, let me take a new slide. Yeah. So right. So this is the circuit we were dealing with, and right now I have taken only the drain to source capacitance, okay, or COSS 1 and COSS 2. This is S1, See, this is S2 and this is S1 and this is VDC. Okay. So, and then right now we are at what point? We are at the point that your entire current is now flowing through the channel of S2. Okay. And S2 is in which region? Is it an ohmic region or saturation region right now? We are over here right now. So S2 is in which region? Is it an ohmic region or saturation region?
Saturation.
Correct. So it's in saturation region. Okay. So now the point is this diode has stopped conducting. This diode has stopped conducting. So what would happen is naturally we told that the voltage across S2 would fall to 0 and voltage across S1 would increase to VDC. But how would this happen is the question. So when you tell that the voltage across a device is falling to 0 or voltage across a device is increasing to VDC, what do we mean? We mean that there is some capacitance which basically COSS over here, right? COSS is actually blocking a voltage of VDC and COSS is actually discharging to 0, right? That is what we talk about. When we tell that the device voltage is 400 volts, it means that the capacitance across the device is blocking 400 volts, right? And another convention that we follow is that if the capacitance is charging, right? If the capacitance is charging, the charging current is like this. And okay, so this is during charging. Okay. And if the capacitance is kind of discharging, then we are taking, so this is plus minus. So if the capacitance is discharging, we are taking out charge. We are taking out charge. So therefore, the direction is like this. Okay. Yeah. So therefore, the direction is like this. Okay. So now when we tell that the voltage across S2 is falling, right? Voltage across S2 is falling, it means that the capacitors is discharging. COSS2 is discharging. Correct. And what about COSS1? COSS1 is charging. Correct. Voltage across S1 is rising, voltage across S2 is falling. And as I told, voltage across S2 is falling as in like COSS2 is discharging. So the discharging current will come like this. Correct? Discharging current will come out like this. And the charging current will go in. Right? Right? Okay. So now can you tell me what will be the path for this current to flow, for the discharging current to flow? So how would the discharging current of COSS2 flow? What is the easiest path? Current always follows the easiest path. So what would be the path for discharging current to flow of
To the S2
COSS2?
switch.
Yeah. So you will see that the current will complete its path through the channel of the switch. Okay, it cannot flow through the diode obviously. So the current will complete its path through the channel of the diode, channel of the switch S2. So COSS2 is discharging through the channel of S2. Okay. And what about S1? How would, from where would this get the charging energy? Right? If you have to dump charges inside COSS1, some active source has to dump the charges, right? So how would the path get completed? The path would be completed from VDC. From VDC, it would go like this. It would come like this. Through COSS1, it would charge up COSS1 and then it would go like this through the device S2 and back to VDC. This is how COSS2 1 charges. So COSS1 is charging through the entire DC DC bus loop. Agree? Right? Okay. So this is how the charging and discharging for, oh my god. So this is how the charging and discharging for COSS1 and COSS2 are going to happen. Okay. So then, yeah. So during this period, right? So let's assume that there is a constant current flowing. The charging current is constant. So we know that I is basically what? I is equal to C dV by dt, right? If I is constant, then dV by dt is constant. So dV by dt is falling at a constant rate. So let's assume for simplicity that your voltage falls kind of linearly because the current is constant, voltage falls linearly. Okay. And as I told you, okay, fine. So what happens to the drain source current during this interval? What is IDS, right? What is IDS? IDS can now be written IDS2, right? IDS2 can now be written as original IL, right? That was flowing through it, plus whatever is the discharging current of ICOSS2 plus whatever is the charging current of ICOSS1, right? So this can be written as IL plus COSS2 into dV by dt plus COSS1 into dV by dt. Do you agree?
Yes, sir. Yes.
Nice. That is why you will see practically, even though we have drawn it like a constant value, you will see practically that the current would be something like this if you measure it practically, right? Current would be something like this. We have assumed constant, so the current should be a square ideally, but you will see that it would be something like this. Okay. So this extra current, right? This extra current that you are going to see over here is contributed by the COSS of both COSS1 and COSS2 charging. Okay, fine. There is one more thing, right? So at this instant, right, when this when the diode stops conducting, when the antiparallel diode stops conducting, this is after all a diode. You know that diode, when it stops conducting, it will not go to zero directly. There will be reverse recovery, correct? When the diode stops conducting, there is going to be a reverse recovery. Okay. Reverse recovery is a negative current between anode to cathode, or it's a positive current between cathode to anode. Yeah. So it is actually a positive current between cathode to anode, right? The reverse recovery. So this is your QRR, right? So this reverse recovery current, you will see this reverse recovery current will also flow through the devices too. Okay. So the reverse recovery current, let me start from here. The reverse recovery current will also flow something like this. Okay. Understood, right? There should be a path for the reverse recovery current. Correct. Obviously, the channel cannot conduct. So it has to flow through S2 only. Do you agree? Reverse recovery current of this particular diode, antiparallel diode of S1. The reverse recovery current corresponding to the antiparallel diode of S1 also has to flow through S2. So plus IRR of S1. Right? This will also contribute to an extra bump. So you will see the current being something like this. This particular region is contributed by IRR. Is this agreed by all of you? Is this fine? So what all components were added during voltage fall period? There is of course COSS loss, right? So I mean the COSS current which has to flow through the device, correct? So this is something like this, and then there is also reverse recovery, right? Reverse recovery of the antiparallel diode, because once the diode stops conducting, there will be some reverse recovery, and that has to flow through the bottom device. Okay, that is why you will see an extra bump if you closely observe the device current. Is this fine so far? Whatever was taught so far, is this fine? We can continue with the numerical problem in the next class. Okay. I mean, we
Okay.
can solve it, but you should understand what's happening, right? Like, I think these three intervals, are they clear? That is
Yes,
especially the
sir.
current rise and voltage fall. Is the concept clear to you guys? So you understand that there is an overlap over here and there is an overlap over here, and these two regions actually contribute to your switching loss during turn on. A similar thing will happen during turn off. Okay, now that you have understood it, in the next class I will directly have a picture of this transient, and from there you can understand. Okay, so is this fine so far to all three of you?
Yes, sir.
uh, like others, Anandi, and is this
So can you
fine?
explain again that how
Which
the
part?
saturation region,
Sir, I have
Sat-
another class.
how that current split into S2 and also anti-parallel diode of S1, then how it blocks the VDC there?
yeah, okay, so you're asking why the VDC is not falling, right?
Yes, at that period, I want to.
Yeah, so this one you understand, right? Initially the entire current is flowing through antiparallel diode of S1. Now what's
Yes.
happening is you just turned on S2, right? So then what would happen?
So,
As you as you know, basically your uh, VGS is now okay. Let me take another slide. So now what's happening? Your VGS was increasing. It hit V threshold, right? And beyond that as well, it continues to increase. Okay. Now we are in the saturation region, right? So we are in the saturation region. So which means that till this point, anyway, the current was zero because VGS is less than V threshold. So this is ID and this is VGS. Okay. So till this point, ID was zero, and beyond that, what would happen? It would behave like a voltage controlled current source, VGS minus VTH, right? At VGS equal to VTH, I channel is zero, right? At VGS equal to, let's say, V threshold is 3 volts, so let's say it is 4 volts. Then I channel would be what? GM into 4 minus VTH, right? And as VGS increases, as VGS increases like this, right? You will see that the drain current will also increase. Agreed? Is this
yes.
fine?
Yes.
Okay. So now let's go back to the half bridge circuit. So in the half bridge circuit, the anti-parallel diode of S1 was conducting, right? I can draw something like this, correct? Anti-parallel diode of S1 was conducting, and um, here the inductor current is coming in, which is a fixed value IL, right? and then over here you are having a current source. This is the circuit, right?
No.
hmm. So this is the circuit that we were having. Correct. So what we told was initially, right? Initially the entire current was flowing through D1. Now what happened after the interval after T1, what happened was this started taking in current. So what happened is this start taking in current as the current increases, right? As the current through this increases like this, proportionately the current through the diode would go on decreasing, right? Do you agree? As
Yes.
ID increases, the diode current would go on decreasing because the total current is fixed, that is IL, right? That is coming to this node. Okay, the total current is fixed. So as this current increases, the current through the diode would go on decreasing. Agreed? Is this fine?
Yes, sir.
Okay. Now you understand initially the voltage across this device was how much? This device voltage was VDC, right? Correct?
Yes.
Voltage was VDC across device S2 initially. So now you just take this diode conduction, right? Just consider this diode conduction. When can a diode conduct? A diode can conduct only when this is more positive than this. That is VA is more positive than VK. That is the anode voltage should be more positive than cathode voltage. You tell me, let's take two scenarios, right? In one case, the voltage over here is VDC, right? And the other one is zero. And in the other case, let's say there is some voltage across this, right? Let's say there is 10 volts across this. So can the diode conduct? Will this be possible in the second case? Can the diode conduct in the second case? Do you understand my question?
Yeah,
So
yes, sir.
take this case, right? Can a diode conduct like this? That is anode is this and this
No,
is
no, no,
cathode.
no, no, no. No.
So the diode cannot conduct if there is some voltage appearing across it, right?
Yes.
Right? So if there is a voltage appearing across a diode, the diode cannot conduct. So as long as this diode is conducting, as long as this diode is conducting, okay, as long as this diode is conducting, there cannot be any voltage. There cannot be any voltage like this, right? There cannot be any voltage across the diode as long as this diode is conducting, right? Do you agree? As long as this diode is conducting, there cannot be any voltage across
Yes.
S1. Is this fine? Do you agree?
Yes, sir. Yes.
So then what would happen? Entire VDC is only appearing across the device S2 and there is no voltage across device S1. Okay. This condition would continue as long as the diode is going to carry some current. When the diode stops carrying current, right? When the current eventually hits zero, right? When the current eventually dies down to zero, only then there can be voltage across this device. Okay. Only then there can be voltage across this device. Do you understand? That is why we told that the voltage VDS will remain at VDC until my drain current reaches the rated current IL, which means that the diode current has become zero. Right?
Yes,
Let
sir.
us say have reached this point, there is no current flowing through the diode. Only then the device can block voltage. Or else, if the device gets any voltage across it, the diode cannot conduct. Right? That is why we tell that the voltage remains VDC across S2. Across S2, the voltage remains VDC as long as this particular diode is conducting. Okay, because simple fact is that any diode cannot conduct if there is a positive voltage between cathode to anode. Between anode to cathode, there should be positive voltage. Between cathode to anode, it cannot block a positive voltage. Do you understand?
Yes, sir.
Right. That is why you are seeing that the voltage remains at VDC
Your voice is
until
not clear, sir.
uh, now is it clear? Is it fine?
No, sir. Still it's not clear.
Yeah. Did you understand like what I was telling during that time?
Yes,
So
sir. I
until
understood.
until the diode conducts, it cannot block any voltage. Adinala, so across the other device, entire DC bus voltage will come.
Okay, sir.
Okay, va?
Yes,
Yes,
sir.
Okay.
sir. That
Ah,
course progress में that problem solving session 50% कामी sir. Any reason, sir?
sorry, course.
That that progress no, the each course progress coming in detail site.
Mm-hmm.
It's showing in problem solving session is 50% only progress. With any reason because I am logging through my name only for all the sessions.
Uh, I don't know exactly these details
Yeah.
actually with regards to the. You can directly mail them in PTEL IIT Madras. They are
Okay. Okay.
resolving queries very quickly. Like I have seen within like 1 hour or 1.5 hours, they will respond during normal
Okay.
work hours. So,
Okay.
yeah.
Thank you.
Okay. So we will conclude for the day and we will meet in the next week then.
Okay.
Okay.